Welcome to the Deep Dive. We're here to sift through the information overload and pull out the real gems, helping you get up to speed fast. Today, we're looking at something literally fundamental, something we use constantly, but maybe you don't think about too deeply, light itself. Yeah, everything from, sunlight to your phone screen. We see it, obviously, but there's this huge invisible world of light impacting us all the time. So our mission today, to really explore what light is, understand it's part of this bigger spectrum, and uncover some, frankly, pretty core facts about how it works. We've got some great source material to guide us. Okay, let's start with the basics. What most people think of as light. From a lamp, the sun usually seems white, right? But here's the first twist. That white light, it's actually not a single thing at all. It's made up of all the colors of the rainbow packed together: red, orange, yellow, green, blue, violet, ROYGBIV. Think about shining sunlight through a glass prism. It splits the light into that band of colors. The prism doesn't make the colors, it just separates what's already mixed inside the white light.
Right, and that separation is just scratching the surface.
Yeah.
What's really fascinating is how, well, limited our own eyes are. If you took that same prism light and used special photographic film, you'd capture way more than we see, a much broader spectrum.
Wow, okay, so our eyes are basically tuned to just one narrow frequency band, is that it?
Pretty much, yeah. We're only picking up a tiny slice of the whole picture.
So what is the whole picture then? What connects the light we see with all this other stuff?
That connection is electromagnetic waves. Things like X-rays, microwaves, radio waves. They all share key properties with visible light because they're all fundamentally electromagnetic waves, part of the same family.
Right, electromagnetic waves. But what does that actually mean? Is it like a wave in the ocean or sound?
Good question. It's a bit different. An electromagnetic wave is what we call a transverse wave. Imagine the wave itself moving forwards, okay? But then you have these electric and magnetic fields, and they're oscillating, kind of wiggling up and down, side to side. And here's the key. These wiggling fields are at right angles to each other, and they're also at right angles or perpendicular to the direction the wave is traveling.
Ah, okay. So the energy moves forward, but the wave part is happening across that path. That's transverse.
Exactly.
So this whole family of waves, they all do that kind of wiggle.
Yep, that's the common mechanism.
Then what makes an X-ray different from, say, a radio wave? Or red light different from blue light?
It boils down to two things mainly: their frequency and their wavelength. How fast they wiggle and how long each wave is. For visible light, those differences give us the different colors. Red has a longer wavelength than blue, for example. For the invisible stuff, those differences in frequency and wavelength define whether it's an X-ray or infrared or a microwave, giving them completely different properties.
Okay, that makes sense. And this leads us to the idea of the electromagnetic spectrum. Reading through the sources, it's clear this isn't like separate boxes. It's more like a continuous gradient, right?
That's a great way to put it, a continuous range. We give names to certain sections, like radio waves or visible light, but there aren't sharp dividing lines. Sometimes the categories even overlap a bit. It's all one big spectrum of energy.
Maybe I can walk through it quickly just to get a feel for what's where.
Sure thing.
Okay, so at one end you have radio waves, super long wavelengths. That's your AM, FM radio, TV signal.
Moving up in energy and frequency.
You get microwaves, used for radar, obviously microwave ovens, even aircraft navigation.
Right. Then comes infrared or IR waves. We feel that as heat, right? But it's also used in thermal imaging, night vision, even physical therapy.
Okay, and then smack in the middle, the tiny part we can actually see. Visible light, photography, seeing the world, microscopes.
Our little slice of the spectrum.
Beyond that, ultraviolet, UV light. Can cause sunburns, yeah,
Okay.
but also used to sterilize things or make fluorescent minerals glow.
Getting higher energy now.
Definitely. Next are X-rays. We all know those from the doctor or dentist seeing bones, also used in cancer treatment sometimes.
Crucial for medical imaging.
And finally, at the very top, the highest energy, gamma rays. They can penetrate thick material, so they're used to check for flaws in structures, and also in some cancer therapies and food irradiation.
It's quite the range.
It really is.
Yeah.
And it's amazing how many of these invisible waves are constantly working around us. Actually, speaking of applications, we found this really cool example, sulfur light bulbs. Have you heard of these?
I have, yeah. They're pretty interesting technology.
Right. Instead of a hot wire like a normal bulb, they use microwaves to basically zap sulfur gas until it glows.
And the light it produces is remarkably similar to natural sunlight. Very full spectrum.
And they're incredibly efficient, like almost 6 times more light for the same energy as a standard 100-watt bulb.
Plus, the bulb part lasts ages something like 60,000 hours, apparently. Though the microwave generator needs replacing sooner.
Yeah, apparently they're too intense for home use right now, but they're lighting up huge spaces like factories and sports arenas. Pretty neat use of microwaves meeting light.
It really shows the versatility across the spectrum. And you know what's truly amazing?
What's that?
All of these different waves, from the lowest energy radio wave to the highest energy gamma ray, they all travel at exactly the same speed
Yeah.
in a vacuum.
Ah, yes, the universal speed limit. The speed of light, often just called seats.
That's the one.
And it's ridiculously fast, isn't it? About 300 million meters per second in a vacuum.
Roughly 3.000 times 10 to the 8th meters per second, yeah. It's so fast that early attempts to even measure it just couldn't. The methods weren't precise enough for something moving that quickly.
Does it slow down at all? Like in air?
It does, slightly. It travels fastest in a perfect vacuum. Air slows it down just a tiny bit, water slows it down more, glass even more. But that vacuum speed is the absolute maximum.
Okay. And this constant speed, see, it connects back to the frequency and wavelength we were talking about earlier.
Exactly. There's a fundamental relationship captured in the wave speed equation.
Mhm.
C equals frequency times wavelength.
So C is the speed of light, F is the frequency.
How many wave crests pass a point per second?
And lambda is the wavelength, the distance between crests.
Correct. And that simple equation holds true for every electromagnetic wave.
Meaning, if you know how fast it wiggles, frequency, and how long the waves are, wavelength, they always multiply together to give you that same constant speed, see?
Precisely. Or, if you know the speed and the frequency, you can figure out the wavelength and so on. They're all locked together. It shows the underlying unity.
Got it. That's a really elegant relationship. Okay, let's shift focus slightly to something we experience every day. Brightness. Why does my desk lamp seem super bright when it's right next to my book? But if I move it across the room, it barely lights it up. It's the same bulb.
Ah, yes. That's a great practical question. The core reason is that light from a source, like your lamp, doesn't just travel in one beam. It spreads out
Spreads out how?
in all directions. Think of it like an expanding sphere of light moving away from the bulb.
Okay, I can picture that. Like ripples on a pond, but in 3D.
Exactly. And because that sphere of light keeps getting bigger as it travels further away,
The light energy gets spread thinner over a larger area.
you've got it. The total amount of light leaving the bulb per second is constant, but it's distributed over an increasingly large surface area the further it goes.
So less light actually hits my book per square inch when the lamp is far away?
Precisely. The perceived brightness depends on how much light energy falls on a given area, like your book page or your eye's retina. And this follows a specific mathematical relationship called the inverse square law.
Inverse square. Sounds complex.
It sounds more intimidating than it is. Basically, it means the brightness you perceive decreases with the square of the distance.
Okay, break that down. Square of the distance.
It means if you double the distance from the light source,
Yeah.
the brightness doesn't just drop by half. It drops to 1/4
Yeah.
Wing2 squared of what it was.
Oh, wow. So double the distance, only 1/4 the light intensity.
Exactly. If you triple the distance, the brightness drops to 1/9, 1/3 squared. It falls off really quickly as you move away.
That explains why even really powerful lights seem dim from far away, like streetlights down the road or stars.
Absolutely. That inverse square relationship is fundamental to how we perceive light intensity over distance.
Okay, that makes a lot of sense. So, quite a journey today. We started with familiar white light, saw it was actually a mix of colors, and then realized that was just a tiny part of a huge electromagnetic spectrum.
From radio waves all the way up to gamma rays.
And learned that all these waves, despite their differences, are fundamentally the same kind of thing, electromagnetic waves, and they all travel at the incredible speed of light in a vacuum.
Related by that simple equation, C equals FA up.
And finally, we looked at why things get dimmer with distance, that inverse square law showing how light spreads out.
Yep, covering quite a bit of ground there,
It really puts light in a whole new, well, light.
and maybe leaves us with something to think about. Consider this. Most of what we know about the universe, especially things far away, comes to us via these electromagnetic waves. Not just the visible light, but radio waves from galaxies, X-rays from near black holes, infrared showing star birth. So the question to ponder is, how has our ability to see in these invisible parts of the spectrum totally revolutionized our understanding of the cosmos? What picture are we missing if we only rely on our eyes?
That's a fantastic question to end on, a reminder that there's so much more out there than meets the eye. That's all for this deep dive. Hopefully we've sparked some curiosity about the amazing world of light and waves.